Snakes are an interesting bunch. They are tetrapods despite lacking legs. To live as a muscle tube, they had to adapt their bodies to work around that lack of limbs. It makes them extremely bizarre, all the way down to the skeletal level. Some are frightening, others are just plain ugly, yet more are some of the cutest, chilliest, most boopable reptiles you will ever meet. Let's peel back the layers and take a look at the bones of snakes and see why it is that they are way weirder than we give them credit for. Snakes are lizards. Sorry if this is the first time hearing about it. Sorry because this is not why we are here today. All living snakes and lizards share a common ancestor and are each other's closest relatives, joined together in the Squamata order. The giant Mesozoic sea reptiles, the mosasaurs, are somewhere in there too, but that's several other videos worth of information. Snakes themselves, all members of the Serpentes suborder, have a complex and tricky evolutionary history. Recent discoveries of proto-snakes have been shedding a lot of light on their evolution, but many questions remain unanswered. But what about the ones we got, the ones slithering with us today? The Serpentes is currently divided into the Althinophidia and the Scolophidia groups. The Althinophidia is the group that contains all snakes that are not blind and thread snakes. This group contains 19 living families, including everything from rattlesnakes to the green anaconda. The Scolophidia is the weirdest of the biggest snake groups in containing only 5 living families and 39 genera. All of these noperopes are the blind and thread snakes. They go by those common names due to how damn small they are. I feel like Microphidia may have been a more fitting name for this group, as they are usually along the lines of 10 centimeters, though some members can reach as long as 100 centimeters or 40 inches. These tiny snakes may be a bit different, at least skeletally, than the rest of the snakes due to their small size, so information on snake skeletons may not completely apply to them. Then again, the same can be said of other snakes, as generalizations are not always great. We shall continue anyways. The snake skeleton, being a tube, basically just looks like someone's spine attached to a nasty jumble of bones we call a skull. There is much more to that, but all the good stuff is in the skull. So let's begin by looking at their prickly noggins. Unlike the skull of frogs, which are adapted to less and less bone and for swallowing things whole in one go, the snake's skull is a very complex structure with numerous joints to allow the snake to swallow prey far larger than its head. The typical snake skull is an absolute bloody nightmare, and this is before we even put flesh on it. If we were not well versed in reptilian anatomy, I could see one easily thinking snake skulls are simply anatomical display pieces. They look like someone took a regular skull and exploded it in the way some museum displays explode a skull to show you each and every segment that makes up a noggin. They're very cool, but not so cool when they're supposed to be like that. With snakes, it's all about being flexible, and flexibility means long stretched out bones, little keeping everything solidly together, and reducing bone where it counts. The entire skull needs to be able to flex many of its parts in order to swallow huge things all at once. Some of us could learn a few things. The snake skull has a solidly ossified brain case. That means the bone surrounding the squishy pink gray matter is hardened or ossified into a solid box to protect those inner bits. They also have united or fused parietal bones extending downward to the basis sphenoid and over the brain case. The parietal bones, these guys here, are what basically make up the dorsal region of the skull, the tippy top, the noggin if you will. In snakes here, they are fused together into one bone. This often happens in many different animal groups to provide more structural support to this part of the skull. It's very important for this part of the skull to be hard to break. It's where the brain is, after all. The basisphenoid bone in reptiles, birds, and many mammals, and in snakes here, is a bone located at the base of the skull. It is immediately in front of the bone that contains the opening through which the brainstem projects to connect with the spinal cord. That's important, I think. The postfrontal bone, if present, borders the eye socket behind and rarely also above, and in the pythons, a supraorbital bone is intercalated between it and the prefrontal bone. The frontal bones, so named because they form the forehead, the front of the top of the skull, are right in front of the snake's parietal bones. They are large, not fused like the parietal bones are, and extend forward into a rostrum extending to the ethmoidal region. The nose region is less ossified, and the paired nasal bones are often attached only at their base. The prefrontal bone is situated on each side, between the frontal bone and the maxilla, and may or may not be in contact with the nasal bones. The maxilla bones are those that make up the jaw parts of the upper jaw in most tetrapod animals. They are located here in snakes and are one of the skull parts that have teeth. Most snakes have teeth on 4 pairs of bones, 2 of which are the same as pairs of bones where humans do, the maxilla and the dentary or lower jaw. In addition, almost all snakes have teeth on 2 bones that in humans form part of the roof of the mouth, the palatine and the pterygoid, which are connected one in front of the other. This means that snakes have 2 upper jaws on each side, an outer one, the maxilla, and an inner one, the palatine and pterygoid. If a snake has fangs, they are always on the maxilla. You can sometimes see this pattern of tooth marks left behind when a non-venomous snake lets go after biting something, and in fact, many resources suggest that you can use the tooth pattern to determine whether or not a bite has come from a venomous snake, since most dangerous venomous snakes have different tooth patterns on account of their fangs, and most of their non-fang teeth don't usually come into contact with the target. The premaxillary bone is single and small, and as a rule connected with the maxillary only by a ligament. The premaxilla, as suggested by its name, is a little bone before or in front of the maxilla bones. In almost all snakes, this bone is small and toothless. It doesn't have as big a function as it does in other tetrapod groups. However, some pythons do have teeth on this part of the skull. If we turn the skull to take a look at the undercarriage, we will meet the next sizzling bone, the vomers. The vomers are a rinky-dink pair of connected bony plates that are also connected to the vomeronasal organ, which is the paired olfactory smelling sense organ located in the moist, soft tissue of the nasal septum, which is in the nasal cavity just above the roof of the mouth. These are extremely prominent in snakes, and is why they have weird holes and stuff in the roof of their mouths, and why they have the forked tongues, and why they stick them out all the time. They taste the air, and the air particles go into the vomeronasal organ so the snake can get an accurate read on where the smell is coming from. I'd say it's weird, but most tetrapods have some form of it, including us. The next rickety bones that make up the underside of the cranium are the palatine and pterygoid bones. They are usually flat plates that make up the roof of the mouth, but snakes had to come along and mess with the formula. They really didn't want to be considered spitters because spitters are quitters, and even Isabella knows this. The palatine and pterygoid bones are long and parallel to the axis of the skull, the latter diverging behind and extending to the quadrate bones or to the articular extremity of the mandible bones. The pterygoid is connected to the maxillary by the ectopterygoid or transverse bones, which may be very long, and the maxillary often emits an obnoxious process towards the palatine, the latter bone being usually produced inwards and upwards towards the anterior or frontmost extremity of the basisphenoid bones. Wondering what some of those anatomy terms mean? So do I, but we will learn here in a moment. The outer and inner upper jaw are connected by a toothless upper jawbone called the ectopterygoid. The ectopterygoid is a palatal bone which, like many palatal bones, may have originally developed as a dermal bone, replacing part of the primitive upper jaw. It is simply another plate of bone connected to the pterygoid bone. In rare cases, such as the snake eater, the Bolemon genus, the ectopterygoid bone is forked and articulates with two branches of the maxilla. The pterygoid bones work like a lever to transfer muscular power from the muscles attached to the pterygoid out to the maxilla, which has no muscles of its own. When a snake is chowing down, the upper jawbone, inner and outer parts, is raised and moved slightly backward, alternating the left and right sides and pulling the prey into the mouth. The characteristic jaw walking or pterygoid walk motion of feeding snakes. So, the front of the pterygoid is attached to the back of the palatine, the ectopterygoid hangs off the outside of the pterygoid, and the maxilla hangs off of the other end of the ectopterygoid. In vipers whose fangs fold, the maxilla and its fang are pushed forward by the ectopterygoid and pterygoid. The quadrate bone is this guy here, which forms the upper part of the jaw joint. The lower jaw articulates at the articular bone, located at the rear end of the lower jaw. The quadrate bone forms the lower jaw articulation in all animals except mammals. In snakes, the quadrate bone has become elongated and loosey-goosey, contributing greatly to their ability to cluck very large prey items. Here in snakes, these bones are usually large and elongate, and attached to the cranium through the supratemporal or squamosal bones. The quadrate and the maxillae and palatopterygoid arches are more or less mobile to allow for the distension required by the passage of prey, often exceeding the size of the mouth. For the same reason, the rami of the lower jaw, which consists of dentary, splenial, angular, and articular elements, with the addition of a coronoid in the boas and a few other small families, are connected at the symphysis by a very extensible elastic ligament. See the space here? In life, there is a stretchy band of stretchy ligaments connecting the two. So, when a snake swallows prey, it technically does not unhinge its jaws. Instead, it rather just stretches the tips until it has a huge lower jaw for sucking down rats or whatever. If we take a real quick look at the lower jaw, we will see that it is composed of the least number of bones out of the whole skull. The bit studded with teeth at the very end is called the dentary. It is connected to the articular bone with the coronoid and angular and splenial bones. However, in snakes, the articular, syrangular, coronoid, and splenial bones have fused to form the compound bone. The lower jaw is suspended from the quadrate bone and articulates at this compound bone. Amazingly, in most snakes, there is no direct connection between the upper jaws and the brain case. Instead, the palatine and maxilla are connected to the brain case by long ligaments, which give them great freedom of motion. The front end of the palatine is connected more firmly to the snout, albeit still with some freedom to move. The rear end of the maxilla is also connected by a ligament to the lower jaw. It's really the movements of the palatine and pterygoid that swallow the prey. The lower jaws mainly press the prey against the upper jaws, and the teeth on the dentary and maxilla rarely contact the prey and play little active role in swallowing. The lower jaws, or mandible, participate in the process of feeding as well. And unlike in humans, they have a loose attachment of the lower jaws to each other at the front of the dentary bones. The dentary bones are connected firmly at the back to the articular bones, which are connected to the quadrate bones at a flexible joint, which are connected to the back of the brain case by the supratemporal bones, also at a somewhat movable joint. Together with the flexible palatomaxillary apparatus, the upper jaws, this three-part lower jaw allows snakes to open their mouths very wide, walk their heads over, and consume things that are as big as they are without breaking them into smaller pieces or using their non-existent hands. The quadrate also attaches to the columella, which is the sole inner ear bone in reptiles. Thus, the lower jaw also conducts sound to the ear. The hyoid bone is a horseshoe-shaped bone situated in the anterior midline of the neck between the chin and the thyroid cartilage. At rest, it lies between the base of the mandible and the third cervical vertebra. In snakes, the hyoid is reduced to a pair of cartilaginous filaments situated below the trachea and united in front. Teeth. In most snakes, teeth are located on the dentary of the lower jaw, the maxilla, the palatine bone, and the lateral pterygoid plate. The latter forms an inner row of teeth that can move separately from the rest of the jaws and are used to help walk the jaws over prey. Several snake lineages have evolved venom, which is typically delivered by specialized teeth called fangs, located on the maxilla. Fangs are always on the maxilla, and that's because the maxilla is the primary prey-catching bone in the snake's skull. As far as we know, fangs evolved only once as enlarged teeth at the back of the maxilla in the ancestor of all living colubroid snakes, about 75 million years ago. In many living species of snakes, this is still the situation, and the vast majority of these are not dangerous to humans, although some can inflict painful bites if allowed to chew for a few minutes, and a few can be deadly. In at least 3 cases, the vipers, the elapids, and the atractaspidids, the fangs have moved up to the front of the maxilla. Most snakes can be placed into one of 4 groups based on their teeth, which correlate strongly with venom and lineage. Aglyphis snakes have no specialized teeth. Each tooth is similar in shape and often size. When teeth vary in size, as in some bird eaters, they do not vary in shape. Most Aglyphis snakes are non-venomous. Some, like Thamnophis, are considered mildly venomous. Ophistoglyphus snakes possess venom injected by a pair of enlarged teeth at the back of the maxillae, which are normally angled backward and are grooved to channel venom into the puncture, like ruffles from hell. Since these fangs are not located at the front of the mouth, as a normal snake should do, this arrangement is vernacularly called rear-fanged. In order to envenomate prey, an Ophistoglyphus snake must move the prey into the rear of its mouth and then penetrate it with its fangs, presenting difficulties with large prey, although they can quickly move smaller prey into position. Imagine that, having to mouth your prey a bit
Good old rub.
before sinking your backshot fangs into the poor little sucker and pumping in your death juice. Nasty business.
Yeah, boy.
The Ophistoglyphus dentition appears at least 2 times in the history of snakes. The venom of some Ophistoglyphus snakes is strong enough to harm humans. Notably, herpetologist Carl Schmidt and Robert Mertens were killed by a boom slang and a twig snake, respectively, after each underestimated the effects of the bite and failed to seek medical help. Ophistoglyphus snakes are found mostly in the families Colubridae and Homolopsidae. Proteroglyphus snakes have shortened maxillae bearing few teeth except for a substantially enlarged fang, pointing downwards and completely folded around the venom channel, forming a hollow needle. Because the fangs are only a fraction of an inch long in even the largest species, these snakes must hang on, at least momentarily, as they inject their venom. Some spitting cobras have modified fang tips allowing them to spray venom at an attacker's eyes. This form of dentition is unique to elapids. Selenoglyphus snakes have the most advanced venom delivery method of any snake. Each maxilla is reduced to a nub, supporting a single hollow fang tooth. The fangs, which can be as long as half the length of the head, are folded against the roof of the mouth, pointing posteriorly. The skull has a series of interacting elements that ensure that the fangs rotate into biting position when the jaws open. Selenoglyphus snakes open their mouths almost 180 degrees, and the fangs swing into a position to allow them to penetrate deep into the prey. While Selenoglyph venom is typically less toxic than that of Proteroglyphs, this system allows them to deeply inject large quantities of venom. This form of dentition is unique to vipers. Exceptions. A few snakes do not conform to these categories. Atractaspis is Selenoglyphus, but the fangs swing out sideways, allowing it to strike without opening its mouth, perhaps allowing it to hunt in small tunnels. The blind burrowing snakes of Scolophidia typically have few teeth, often only in the upper jaw or lower jaw. So, there you have it. The snake skull is divided into 4 functional units: the brain case, the snout, the palatomaxillary apparatus, or upper jaws, and the mandibular apparatus, the lower jaws, each of which can move independently. Well, except for the brain case, which is relatively stationary. The upper jaws are divided into 2 partially separated structural functional units: a medial swallowing unit, and a lateral prey capture unit, both of which work with the lower jaws to accomplish their tasks. Onto the rest of the snake skeleton. Vertebrae and ribs.
This is where the fun begins.
The easiest to explain bit of a snake's anatomy is their skeleton. It's also the second thing that makes them weird, though it is the most obvious. The snake vertebral column consists of an atlas vertebra, composed of 2 vertebrae without ribs, numerous precaudal vertebrae, all of which, except for the first 3, bear long, movable, curved ribs, with a small posterior tubercle at the base. The last of these ribs are sometimes forked, 2 to 10 so-called lumbar vertebrae without ribs, but with bifurcate transverse processes, which are called lymphopophyses, enclosing the lymphatic vessels, and a number of ribless caudal vertebrae with simple transverse processes. When bifid, the ribs or transverse processes have the branches regularly superposed. To be more clear, cervical refers to vertebrae of the neck, dorsal to the back, sacral to the pelvis, and caudal to the tail. Bifid refers to an object that has 2 splitting projections from a single unsplit body. The centra, or middle part of the vertebra, have the usual ball and socket joint, with the nearly hemispherical or transversely elliptic condyle at the back, a condition which is called procoelus, while the neural arch is provided with additional articular surfaces in the form of pre- and post-zygapophyses, broad, flattened, and overlapping here, and of a pair of anterior wedge-shaped processes called zygosphene, which are right here, fitting into a pair of corresponding concavities, zygantrum, just below the base of the neural spine, right about here. Thus, the vertebrae of snakes articulate with each other by 8 joints, in addition to the cup and ball on the centrum, and interlock by parts reciprocally receiving and entering one another, like the mortise and tenon joints. The precaudal vertebrae, those before the tail, have a more or less high neural spine, which may be expanded and plate-like above, and short or moderately long transverse processes to which the ribs are attached by a single facet. The centra of the anterior vertebrae emit more or less developed descending processes, or hemopophyses, which are sometimes continued throughout, as in Vipera and Ancistrodon, among European genera. If you thought the entire snake skeleton was just body, you'd be incorrect, as they also have tail vertebrae. They only lost their limbs, not their tails, though in many snakes that tail is highly reduced to just a bit at the end of the body. This is probably because snakes use the muscles and scutes under the belly to move around, and the tail doesn't really have the same kind of mechanisms going on. In the tail, or caudal region, elongate transverse processes, these things sticking out to the sides, take the place of ribs, and the hemopophyses are paired, one on each side of the hemal canal. In the rattlesnakes, the 7 or 8 last vertebrae are enlarged and fused into one. Limbs? I barely know her. No living snake show any remains of the pectoral arch, which is a bony arch formed by the collarbones and shoulder blades in humans, or just simply referred to as the shoulder girdle across tetrapod groups. However, remains of the pelvis are found in boas and pythons, a long ilium attached to the lower branch of the first bifurcate transverse process of the lumbar vertebrae, bearing 3 short bones, the longest of which, regarded as the femur, terminates in a claw-like pelvic spur, which usually appears externally on each side of the cloaca. These snakes use them for sexy time. Pelvises, pelvisi, or pelvises? The pelvic girdle. The thing the legs attach to. This thing. This is typically made up of 3 major bones across the tetrapod animals. You have the ilium, this thing here, the pubis, this long boy here, and the ischium, this guy over here. This arrangement is molded and adapted according to the group to which it belongs. The dinosaurs have the nicest pelvis in my opinion, as you can easily point out all 3 bits. Humans have the worst ones because we had to adapt to being bipedal and upright. These pelvic bones are also found in the Leptotyphlopidae, with an ilium, pubis, and ischium, and rudimentary femur. The ischium forming a ventral symphysis, as well as the Annelidae and Typhlopidae groups, with the Typhlopidae retaining only a single bone on each side. At various points in the evolution of snakes, some had limbs, some had usable limbs too. The super special example of this used to be the supposed four-limbed snake Tetrapods, but it turned out to be more likely part of a squamate group called the Dolichosauridae, a group closely related to mosasaurs and snakes, but is technically neither. If you want to know more about this new case, check out my video on the topic, links in the description and comment section below. As such, there is currently no known, totally four-limbed snake or proto-snake from the fossil record, but there are plenty of two-limbed snakes. Najash is a late Cretaceous South American form that carried a pair of functioning but diminutive hind legs. Some other fossil snakes are known to have possessed hind limbs, but their pelvic bones lacked a direct connection to the vertebrae. These include the likes of Haseophis, Pachyrhachis, and Eupodophis, which are slightly older than Najash. At some point, the common ancestor of snakes and lizards had to have had full working limbs, but transitional examples of such have yet to be found. As such, the evolutionary story of the snakes is a little up in the air. Though one hypothesis may be more heavily supported by the data, there are multiple hypotheses that may explain the evolution of snakes. One posits that they originated from a group of burrowing lizards. Another suggests they are more closely related to mosasaurs, with their adaptations a result of marine habits, while genetics seems to suggest that mosasaurs are more closely related to snakes than they are to monitor lizards, suggesting a more complicated series of events that resulted in our modern menagerie of snakes. That's about all I have for you on the wackiness of snake skeletons. They are not the first group to become worm-shaped, and won't be the last, as it is a very common one. Snakes definitely make being this shape weird, in how they have adapted to deal with no hands. They are extremely successful animals, despite being biological socks, and may very well outlive many other groups of animals that we might consider ultimate survivors, like the sharks. I wonder what kind of messed up skeletons we will get to explore next. Stay tuned. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, hit the bell icon for updates, like this video, and drop a comment in the comment section below. Thanks for watching. Special thanks to my elephant tier patrons: Arda Bayer, Biotiverse, Christoph Hubinger, Dinosaur, Isaiah Garza, P.A. Brew News, Ray, Rudy Redgrave, Smiling Walrus. And another thanks to my Tyrannosaurus tier patrons: Iberospinus, Iron Bladesman, Swaffles is Weird, Teeny Dragator, The Dogman,